In the last unit, we completed the descriptive statistics, and we're now moving on to inferential statistics. So inferential statistics is a part of statistics where you make statements about the world and also a statement about uncertainty. So you can make a quantitative statement and then follow that up with something like, I'm 95% sure that I'm right about that. So that is very nice and powerful, and the basis for this is the Central Limit Theorem. So I explained to you what that is, how that works. We look at normal distributions, where they come from, some of smaller effects, and also assumptions of normality in this video. So if you're a researcher, quantitative ecologist, and you go out and measure things in the real world, it's quite striking that normal distributions seem to be everywhere. So if I measure tree heights, for example, or dBH or wood density or whatever it is, these histograms, they look like they have been developed with a mathematical formula. So they're often a perfect match to normal distributions. And that applies to any kind of complex trait. So if you measure physiological traits, leaf area index, frost hardiness, drought tolerance, disease resistance, so they're almost always normal. They are not always normal. So disease resistance can be such a trait that may not be normally distributed. So any complex traits, they tend to be normally distributed, and traits that are maybe just controlled by a few factors, like if you have, for example, a major resistance gene that is responsible for this, then those distributions are not perfectly normal. So in order to get to why that is, you can think of another kind of sampling. So each of those trees that we had here in our population, that tree itself samples the environment and samples the gene pool. So there are many small effects that make the traits of the tree what they are. So there are probably on the order of dozens to thousands of genes that influence a particular trait. And there are also many small environmental factors that contribute, for example, to the height of the tree over the lifetime of the tree. So every day there is a small environmental effect, the amount of sunshine, the amount of water, the temperature experienced by any particular tree that accumulate over time. And as soon as you have a mechanism where you have an integration of many small effects over time, and those represent in a way a sample of the total genes that are out there and the total environmental conditions that are out there, you get those normal distributions. And again, that only works if the sample size is large. So if you have only one factor, like a Mendelian trait, for example, you have flower color that's either pink or it's white, then you don't get normal distributions. And the same if the sample sizes are small, those sample sizes here, so if there are just a few genes responsible for a particular trait, also then you don't get normal distributions. But as soon as you go into the 30s, 100s, those will start to be normally distributed. So if you have complex traits like height or leaf area index of a tree, that is the sum of possibly millions of small effects integrated over time. All those traits will have perfect normal distributions. So just for fun, we could simulate that in R, and I take a slightly different example. Let's work with birds. Because they have this nice random behavior, they fly around. So let's see how a bird population may acquire a trait that's perfectly normally distributed. So let's start with a bird population that's completely empty. So I just wrote my bird population as an empty vector, so concatenate nothing. And if we look at it, there's nothing in there. And let's imagine they go out every day and find some food, and someday they're unlucky, they get nothing. Another day they're lucky, they get food that's equivalent to 5 units of nutrition or calories or whatever. So let's create this food vector. And what I'm going to do now is over the course of the year, 365 days, I'm going to sample this food vector. So this is what they get to eat every day. And so let's run this. And so I put this whole command in brackets, so I always see the output. So these are 365 random numbers between 0 and 5. So that's what the bird is going to eat every day. And that's what that trait is based on. So the total sum of all that food, that may be the weight of the bird or the size of the bird, divided by some factor, obviously. And so I'm going to add this bird to my bird population. So if we look at the bird population now, it's just that 913. And I can run this again, the whole thing. And now I have another bird that's 928 grams in weight. And so on and so forth. So I can do this as many times as I like. And I can look at a histogram. It's not quite a normal distribution, but we haven't run this often enough. So what I'm going to do is I'm going to put a loop around this. So this says for I in 1 to 10,000, just to save me some clicking here. We want to do this. I'm going to indent this a little bit so that we know all this. All this is within a loop. And we're going to add 10,000 birds here to our population, all based on the same mechanism of eating for a year. And now we'll look at the histogram, and it is a normal distribution. So as expected. Let's modify this a little bit. I told you before that if we just have a small set of genes for some disease resistance or something, that may not be normally distributed. So I do have a vector for genes here. I'm just going to put this here to the top, and I'm going to modify my code a little bit. So instead of food, we're talking now about genes. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to change this to 9. So we have one major resistance gene here, and then a bunch of small effect genes. It's very typical for those kind of traits. And we only sample 2. We sample a mom and a dad. So this is not a particularly big sample size, and for that reason, we may not get a normal distribution. So let's take a look at this. First of all, let's clear our bird population to nothing. Run the gene vector, and now we do the 100,000 iterations to create our bird population with various combinations of genes. And if we look at the resulting distributions, so that's not normal. So you have a few lucky ones who got 2 major resistance genes from the mom and the dad, then some who got a resistance gene plus something else, and then you have a majority that's susceptible to that disease. So that can happen. You get these funny distributions sometimes. That usually indicates that this is not the integration of hundreds or thousands of small factors, but just a handful. So you can think of that as a very similar mechanism to the sampling that we did as scientists. So the sampling that we did down here, an investigator looks at particular trees and calculates the average. So that is equivalent to summing up many small effects and dividing by n at the end to calculate the mean. So whatever creates normal distributions here, you would think that this type of sampling also creates normal distributions, right? So even if your original data were not normally distributed, you might actually get normal distributions in your sample statistics. And so just to have an example for the sake of the argument, let's imagine these scientists here, they did not care about the age of the trees. They just sampled any tree. Then my distribution would probably not be normal. So I have always lots of small trees, and as the stands age, the trees grow up and outcompete their neighbors. You will have less and less large trees. So this is how it would look like over the entire landscape of a particular ecological region. So if I were to sample randomly from this, and I did this over and over again, and let's say it's a really important problem, you make some statement, if somebody else disagrees, they go out and sample again. And so just for the sake of argument, assume that 1,000 scientists go out there and each of them samples, 50 trees, calculates the mean. What would you expect? How would those means be distributed if you were to plot them on a histogram? So to find the answer to that question, we could simulate that in R. We've done something very similar before, but there's actually a nice visual simulator on the web that you can use, tinyurl.com CLT simulator as a shortcut that brings you there, and you can just hit begin, and this will bring us to this page. So this is the equivalent of our population of trees. We said in R before, we said we have 100,000 trees with an average height of 15, and a standard deviation of 3. And we could now go ahead and take a sample from that population to estimate the mean and the standard deviation or whatever statistic you're interested in. So let's try this. We can do an animated sample here. The sample size is set to n equals 5. So let's see how that looks. 1, 2, 3, 4, 5. And we calculate a mean from this. So that's my first mean. Now another scientist goes ahead and does a similar study to confirm our results. So we'll do this again. And we'll get a second mean. So not exactly the same. It's a random sampling process. So each time you repeat this, you get a slightly different answer. So there is certainly uncertainty in our results if our sample size is just 5. Now I can take a shortcut here. I can do this 10,000 times. So what you find is that the distribution of my means is approximately normally distributed. It's actually t-distributed. We covered this in the previous video already. And we can now go ahead and test what would happen if my distribution is originally not normal. So we said in our example that we have lots of small trees and a few bigger trees. So what would happen now? Let's clear our set here. What would happen now? What would you expect the distribution to look like? Let's do an animation. Let's do this again. So just from your intuitive sense, how is this going to look like? Is this just a miniature version of the one above? What's going to happen? So let's try this 10,000 times. And I get something that is not quite normal, but pretty close to normal, right? So that's interesting. It depends a little bit on the sample size. So if your sample size is really small, you get skewed distributions. So let's try this again, 10,000 times with n equals 2. So that's where you can get actually your means, the distribution of your means has a skew. But if your sample size is large, let's try n equals 16, 10,000. That is almost a perfect normal distribution. Let's try 10,000 times. So this is also pretty normal. That's interesting, right? So even though your original data that you actually have in your data table might be completely skewed, your distribution of the means is not. And that is true for the weirdest distributions, right? So let's clear this and try something really outlandish here. So if we had something like this and we take 10,000 samples, it doesn't matter, perfectly normal. Okay, so we now have our answer. What would happen if we were to repeatedly sample this population here, even if the distribution is not normal to begin with. My means that multiple investigators would get if they repeated this study over and over would be approximately normally distributed. So that is what the Central Limit Theorem states. When independent random variables are added, their sum or average tends toward a normal distribution, even if the original variables themselves are not normally distributed. And so this central limit theorem has two applications. So one is, so it explains why you have normal distributions in the first place. So it's the integration of many small effects on individuals that lead to normal distributions of their traits in a population. And the application number 2 would be that repeated sampling leads to normal distributions of sample statistics, like the mean, unless the sample size is very small. So then you have to be a bit careful, but as soon as your sample size is even 5 or 10, you've seen it, you get pretty good normal distributions. Okay, so that's a central limit theorem. And, if you're thinking, well, that application 1 seems kind of interesting, but the repeated sampling here, what's this? That seems to be far-fetched. But you'll see in the next video, this is actually a key foundation for all of statistics. So we'll get there shortly. I do want to finish this video by also saying what's not expected to be normally distributed, because that's a common perceived issue. So if you're mixing apples and oranges, your data is not necessarily normally distributed as a whole, right? So let's say we have some pine trees and some spruce trees, and we have two normally distributed traits. If you have those all in one data table, you surely have a bimodal distribution, but that has nothing to do with the assumption of normality not being fulfilled. So if your predictor variable is a class variable, if you have any kind of experiments with any kind of effect, you wouldn't expect your variables over the entire experiment to be normally distributed. So they should actually have some kinks if you have any treatment effects. The other case that's perhaps a little more subtle is if you sample different environments, different ages, or different developmental stages. So if your predictor variables are continuous and not a class variable like in an experiment, so you can have the situations just like we had that in the example above. So different age classes would give you distributions that are highly skewed. That's also okay. The key when you're talking about assumptions of normality is that your response variable needs to be normal for a given set of predictor variables. So given certain environments, given certain treatments, is your response variable normal? And the other big takeaway from this video about the assumption of normality, which we get into later in more detail, is that the sample statistics need to be normally distributed, not your original variables. So it's usually not a concern if your original variables are not normally distributed, if the sample size is reasonably large. We've seen it. So if you have a sample size of 10 or 15 even, your sample statistics are normally distributed, and then your statistics will work just fine. So that's an important piece to keep in mind. Not everybody knows that.